Remember left Riemann sum. Here's what we're going to do. That means you're going to start at the left side of your interval. So a left Riemann sum, we're going to start it at the 50.3, times it by 2, plus 14.4, times it by 3, plus 6.5, times it by 5. That's how I got those numbers right there. Let the calculator do the work for you, and it will give you that. And this is the approximate volume of the tank, indicate the units of measure. And so they tell us the area here is in square feet. So that's going to be cubic feet for our units there. If they did say right Riemann sum, you start at the right side of the interval. You start at 2.9 times 5 plus 6.5 times 3 plus 14.4 times 2. That'll be a right Riemann sum. And then letter B, it says, does that approximation, is that an overestimate or an underestimate? And then explain your reasoning. Okay, here's what we're going to need to do. We're going to need to say what this function is doing, increasing or decreasing. And we see from the table of values that that's a decreasing number. Here's why this is going to make sense. All right, now notice my work, I got an overestimate since A is decreasing. Let me explain why that makes sense there. I did that left Riemann sum without a picture, but if you do a picture, and even if you don't even use those exact points, you just need to know whether it's increasing or decreasing. That's it. And so you could just look at the values. If you didn't do a picture, who cares? Those are decreasing. So if you have any decreasing curve, the concavity doesn't matter whether it's concave up or concave down. Both of those are decreasing, right? Now, if I do a left Riemann sum means you start at the left side of this interval. So you would start here and you would go up to the curve, and then that's where you would draw your height of your rectangle over. And then you go up to the curve, draw the height over, up to the curve, draw the height over, up to the curve, draw the height over, and then see how those rectangles are above the curve. Even if it's concave down, it doesn't matter. If you start at the left side of the interval, because it says left Riemann sum, you start at the left side of the curve, you go up to the curve, draw the height over, and then you go up to the curve, draw the height over, up to the curve, draw the height over, and see how those rectangles are all above the curve. So that's why a left Riemann sum on a decreasing function is an overestimate. They don't want to hear because the rectangles are above the actual curve. They won't give you credit for that. You got to tell me what that thing is doing, whether that's increasing or decreasing always. And then just the opposite would be true if it would be a right Riemann sum. Right Riemann sum, you start at the right side of the interval, you would go up to the curve and then boom, draw the height over, up to the curve, draw the height over, and see how those rectangles, you're missing all that little extra space. The right Riemann sum would have been an underestimate. That's just on a decreasing function. On an increasing function, right, then it's the opposite. So like a left Riemann sum, your rectangles will be below, that'll be an underestimate. And then a right Riemann sum, your rectangles would be above, it'll be an overestimate. So I don't really take a chance to memorize that incorrectly. I just kind of look at what my values are doing, and I'll just draw a general picture real quick. Sometimes I can plot a few points if I wanted to, but usually I just do a general curve because it doesn't matter about that concavity. But that's the justification that we want to practice and we want to be perfect on. That's kind of, if you look at my work here, that's what I was doing to the side. I just drew it in decreasing function, and then I show that those rectangles were above the curve, and then I just put overestimate since that A is decreasing. All right, now letter C. It looked a little funky at first. I was like, what's going on here? The thing is, we have no idea what the shape of this tank is. Just as we got these weird cross sections, and it's getting bigger or getting smaller as you go up the height of that thing. And here it gives us the area of the horizontal cross section is given by that. So that's the area of our cross section, and we want to find the volume of the tank. Now, remember your cross section. When I saw the word cross section right there, I was thinking, oh, maybe I'll do cross sections. And when we find volumes by cross sections, what we always do, we integrate the area of your cross section shape. And here they flat out told us what that area was. So I just integrate that f of h. That's all I got to do. So again, cross sections, you integrate the area of your cross section shape. They tell us what that area is. And then so you just integrate that area. So you integrate the f of h in between 0 and 10, because that's what your function is going to. And then that's a Math 9 calculator problem right there to get that answer. And it does tell us its volume, indicate the units of measure. So it's going to be cubic feet. Another way you could think of it, as you know, you're integrating the area, even when you do the disk method, right? You do pi times the capital R squared, that's the area of that bigger circle. And then you subtract out the pi little r squared, that's the area of that little hole that you subtracted out. But you're integrating the area, but it's that added dx or dy that kind of gives it that added dimension and turns it into a volume for us. Okay, last part of this. says water is pumped into the tank. When the height of the water is 5 feet, the height is increasing at a rate of 0.26 feet per minute. Right when I read that second sentence there, I thought this looks like a related rate problem right there. So when they told me the height is equal to 5, the height is increasing at a rate, that means the dHdt is this 0.26 right there. So that's why I kind of got it down. The dHdt is 0.26 foot per minute when the h is equal to 5. And you want to find the rate at which the volume is changing with respect to time. So we want to find the dVdt. So all of that I kind of thought in my head as I was reading that problem. And then what I needed, I needed a volume equation, and I needed to take the derivative of that. So that was the trickiest part to me, was just, deciding this. And it does give us a hint. It says use your model on part C. This is your model on part C. When you integrate the area, you're going to get the volume, right? So when I integrate F, I'm going to get the volume. Just right now, we don't know what the height, it wants to, it says like when the h is equal to 5, when the h is equal to 7. So we want like a general equation here that doesn't stop at 10. So I'm just going to do the same thing. So I'm going to integrate the F. And then I'm gonna, instead of stopping it at 10, I'll just stop it at a random like height value right there. All right, so I'll just use that as my variable with the h there. Now, first I had like f of h dh in there. It's not a huge deal. You're still gonna get like the same answer and the same work and stuff right here. But technically, once I wanted that h right there, technically you can make those a different letter. All right, a little technicality there. But the point is, when you integrate the f, that's going to give you the volume, right? So I got my volume equals the integral of f. And I just got an h right there instead of a 10 because we just want to go to a random height, have an equation for just a general height. And then when now you do your related rate problem, you're going to do the derivative. So the derivative v with respect to time is dv dt. And then remember your second fundamental thermocalculus. You can rewatch that video I gave you when we first started our review. When you do the derivative of an integral, you're going to get that inside function. That involves just taking that and plugging that in right there, and then timesing it by the derivative of that piece, right? And so like if that was like an h squared, you'd have like a 2h dht. So I took that and plugged it in using my second fundamental thermocalculus, so that I gave me the f of h, and then I know the derivative of the integral is just that inside function. So we're going to get f of h, but then you times by the derivative of that to get that dHdt. You're doing derivative of h's, so you tag on the dHdt, and then you kind of needed the dHdt in there anyways. So I thought that was a little bit funky at first, but then I was like, I gotta work in a dHdt because it tells me how fast that height is increasing. So that's why I kind of knew to put that in there for sure. And then it says when h is equal to 5. So you plug in the 5 for the h's now, and then they told us the dHdt was a 0.26, and now f of 5, you gotta take that 5, just plug it into that f equation for the h, and then plug that into the calculator and you get that number. And that's how fast the volume is changing. So it's going to be cubic feet per minute right there. Choir.